Thanks for clicking on this Narculus production. Today we're going to talk about the first derivative test. So for the next few sections, our goal is to be able to graph any function without the use of a graphing calculator. So we're going to have to use the derivatives of these functions to get information about what the function might actually look like. So that's the goal here over the next few sections, and it starts here with the first derivative test. Most of this you actually already know. You don't know how to do it algebraically, but you already have an idea as to how this whole thing is going to work. So let's get started and see what we can come up with. Okay, so in the last section, one of the last things that we did in the last chapter was we learned how to graph a function, well, without a calculator. That's the goal. But we took a given function called f of x and then sketched what its derivative would look like using the tangent lines to that graph. So let's go ahead and remember what we did in the a couple of sections ago and use that to our advantage. So the first thing we looked for to find points on the derivative was we looked for where there were relative mins and relative maxes, right? Because the slope of the tangent line, we know there, is going to be a 0, which means that the y value's derivative, or the y value of the derivative, will also equal 0 there. So there's one here, and then here's another place where the slope of the tangent line comes out to be 0. So I know that the derivative will be 0 there. So let's put our first 2 points for the derivative on this graph right here. Same graph. Okay, now the next thing we did was we looked at the slopes of the tangent lines. Okay, we looked at the slopes of the tangent lines. So the slope of the tangent line on this side here, they're all positive. They're all greater than 0, which means that my derivative value is also greater than 0. I know that for certain. Okay, so I know for certain that my graph is going to start up here above the x-axis. The derivative y values are positive, and they're really steep at the start, and then they make their way down towards 0, which makes sense because it's got to go through this point here at 0. Now, in the middle, in between the two, the relative min and the relative max, I'm drawing more tangent lines, and all these tangent lines happen to be negative, right? They have a slope that's negative, okay? Slope is derivative because, well, derivative of tangent, slope of tangent line is derivative. So I know that my derivative value here is going to be less than 0. It starts off not very steep because I'm close to 0. It gets a little more negative in the middle, but then comes back towards 0 again because it's got to go through that point. And then finally, I have all these slopes of the tangent lines are positive. So I know the slope of my tangent line here is positive. So I know the y value of the derivative is positive, right? Because derivative just means slope of tangent line. Okay, so they're not very steep at the start, which makes sense. But then they get steeper as they go, and this graph goes away, and off it goes. And that is a sketch of f prime. So that's what we did in the last chapter. We used f to get a sketch of f prime. Now the goal here is to try to reverse that idea, where we would use f prime algebraically and try to get information about f. All right, so now let's take a look at this graph here, because some of the things that you see here are things you probably should already know from pre-calculus, and if you don't, well, we'll remind you. So if you see here on this end as well as this end, the slope of the tangent line is positive, right? The derivative here on both of those places is bigger than 0. And the slopes of the tangent lines are positive because f is increasing, right? So when you have a graph of f, my graph that's in blue of f of x, when the tangent lines, the slopes of the tangent lines are positive, then we know that f is increasing, right? F is increasing because the graph has positive slope, okay? In the middle here, between these two zeros, or between the min and the max, I can see that f is decreasing. So when f is decreasing, we can see that f prime is negative, right? F is decreasing. Why? Because the graph has negative slope. Okay, because the slope of the graph is negative. All right. So these are two things that are going to be important here in the first derivative test. We know that if the derivative's value, y value, is positive, then the function's value, f, is increasing. And vice versa here, we know that if the derivative, the y value, is negative, then that's going to mean that f is decreasing. All right, and you can see that. It doesn't matter what I draw. I could draw anything I want. Okay, here's another curve, whatever you want to call it. It looks different. But again, this graph, here's f. This is f of x. Whenever f is increasing, the slope is positive. Whenever f is decreasing, the slope is negative. Here, f is increasing, the slope is positive. F is decreasing, the slope is negative again. So it doesn't matter what the graph looks like, okay? If f is increasing, then f prime will be positive. If f is decreasing, then f prime will be negative because f prime means slope, right? And we know that if f is decreasing, it has negative slope. Okay? All right, so now let's talk about what we can gather from graphing the derivative. We know if f is increasing, then the slopes of the tangent lines are positive, so f prime is positive. If f is decreasing, then the slopes of the tangent lines are negative, so f prime must be negative. If f has a relative min or a relative max, then f prime is equal to 0 or could be undefined at that value, right? We looked at that when we did the graphs. If I graph the absolute value graph, okay, if I call this f, well, this is a relative min, but at this point, f is not differentiable, right? Because there's two slopes there, okay? So it is possible that if f prime is undefined, f could still have a relative min or relative max there. All right? Now, to analyze these functions algebraically, to use the derivative to get information about f, we're going to look at the converse of all of these things. Now, remember, converse, back from geometry, means that you're going to flip the if-then portion of the statement. Okay? We're just going to flip it around. So, this is really my first derivative test. If f prime is a positive value, if f prime is positive, then f must be increasing. If f prime is negative, then f is decreasing. If f prime changes from positive to negative, all right, well, let's analyze that a little bit. If f prime changes from positive to negative, then f changes from increasing to decreasing. So if f changes from increasing to decreasing, it looks like that. Well, then f will have a relative max at that point. Sure. We agree? I mean, take a look. If f prime changes from positive to negative, when f prime's positive, f is increasing. When f prime's negative, f is decreasing. So if f changes from increasing to decreasing, up to down, then f has a relative max there. And then just the opposite way, if f prime changes from negative to positive, so then f would change from decreasing to increasing, down to up, then f has to have a relative min at that point. Well, sure, of course it does. Okay, just looking at the picture here. All right, so the bottom two things here are really the first derivative test, actually. Okay, these two lead to the first derivative test, but there's certainly things that we're going to analyze here when we use the first derivative test. All right. Okay, so here's really the cookbook for how to do this. All you're going to do is find the derivative of whatever function's given, find the x value where the derivative is equal to 0 or is undefined. They are the critical numbers, right? We did this in an earlier section, okay? The locations of possible mins and maxes, extrema. Then what we're going to do is we're going to test x values on either side of the critical values in the derivative and figure out what signs we get. positive or negative on that interval. That will tell us whether or not f is increasing or decreasing on that interval. Then we can figure out if the critical numbers are mins or maxes, relative mins or relative maxes. Not absolute mins or absolute maxes. That is a different question. Okay? All right. Let's take a look, and we'll give this a shot here. So I want you to figure out where this function is increasing or decreasing. So here's my function f. To figure out where f is increasing or decreasing, I'm going to find the derivative of it. So the derivative here is just 3x squared minus 12x plus 9. I can take out the 3. It's a GCF. And I'd be left with 3 times x squared minus 4x plus 3, which conveniently I'm sure will factor. And it, not like that. It doesn't. Minus 3 minus 1, right? X minus 3, x minus 1. Is that equal to 0? Okay, we're going to split these and solve them. You get x equals 3 and x equals 1. These are my critical numbers. All right, we did this when we did absolute min and absolute max. These are my critical numbers here. So now, rather than take these and plug these into the original like we did when we found the absolute min and absolute max on a closed interval, okay, what we're going to do is we're going to make a number line. And on my number line, I'm going to put these two values. So I have 1 and I have 3. It divides my number line into 3 intervals. Negative infinity to 1, 1 to 3, 3 to infinity. So what I want to do is I want to determine the sign of f prime so that I can figure out the behavior of f. So to figure out the sign of f prime, you're going to pick a test point, any test point you want. So I'll pick somewhere between negative infinity and 1. So I'll pick 0. Okay, I'm going to take 0. I'm going to put it into the derivative. All right. All I care about is the sign of the answer. I don't care what number I get. I just care about the sign. So if I take 0 and plug this in, I have 3 times negative 3 times negative 1. So that's going to be a positive value. So f prime here is greater than 0. All right. Now I'm going to pick something between 1 and 3. I'll pick 2. So if I pick 2 and plug it in, I get 3 times 2 minus 3. That's negative 1. So that's positive, negative, positive. 2 minus 1 is positive. So positive times positive is a negative. So f prime is less than 0 there. And finally, I'm going to pick a number between 3 and infinity, like 4. And if I plug it in, I get 3 is a positive number. 4 minus 3 is positive. 4 minus 1 is positive. Positive times positive times positive. F prime is greater than 0. It's positive. So now what does this tell me? Well, if f prime is positive, then f is increasing. If f prime is negative, then f is decreasing on that interval. And when f prime is positive, f is increasing again. So now, what about I just figured out the intervals of increasing and decreasing, but let's take it one step further and look at these two critical numbers here, 1 and 3. The graph here is increasing before it, then it's decreasing after it. So 1 is a relative max. Then the graph is decreasing and it's increasing. So 3 is a relative min. So now I need to summarize my answer. You cannot use a number line on the exam as a response. Okay? Cannot use a number line on the AP exam as a response. You need to summarize what you have. So from negative infinity to 1 and from 3 to infinity, this graph is increasing. Why? Because f prime is greater than 0. There's your explanation. This graph is decreasing from 1 to 3 because f prime is negative, less than 0. There's a relative max at the point 1, comma. Now, to get the y value, I need to plug 1 into the original f of x. Remember, you're trying to graph the original function at the end of the day. That's the goal here. So that comes out to be 5. 9 minus 6, 3, 5. There's a relative max at 1, 5. Why? Because f prime changed from positive to negative. That's y. And then there's a relative min at the point 3, comma. I'll have to plug 3 into the original. I'll come up here. It's 27 minus 54 plus 27 plus 1. So it's 1 because f prime changed from negative to positive. And again, all your explanations here have to come from the first derivative because this is called the first derivative test. The first derivative is what determined the behavior of f. So your explanations need to reflect f prime. Okay? So there's an example of everything done for you. All right, let's do the same thing here. So the derivative is just 30x to the fourth minus 30x squared. Okay, so now I can factor. Let me do that. I'm going to take out 30x squared. Leave me with x squared minus 1. I can factor the x squared minus 1, or I could solve it. It doesn't make a difference. X minus 1, x plus 1 is equal to 0. I can split these 3 up. This one gives me x equals 0. This one gives me 1. This one gives me negative 1. So on my number line now, I have from negative infinity to negative 1, negative 1 to 0, 0 to 1, and then 1 to infinity. I'm trying to figure out the sign of f prime so I can figure out the behavior of f. Okay, I'm going to pick a test point between negative infinity and negative 1. All right, now, before I do that, before I start picking test points, this value here, when I plug in for x, is always a positive number, right? So I don't really care about this value. This value is actually irrelevant to me. It's only plugging the test point into these two values, or these two expressions here, that are going to give me the actual sign of f prime. So I'm going to pick like negative 2. It doesn't matter. You can pick anything you want. So that's a positive. Negative 2 minus 1, negative. That's also negative. Negative times negative, that's a positive. So f prime here is greater than 0. Between negative 1 and 0, pick like negative 1/2. We're going to have a negative in this term, a positive there. So f prime is going to be negative. I'm going to pick 1/2. That's going to be a negative there and a positive there. So that's also going to be a negative. Okay. And then at 1 to infinity, I'll pick 2. So that's positive, that's positive, that's positive. Okay, so now my behavior of f. Behavior of f. When f prime is greater than 0, then f is increasing. When f prime is less than 0, f is decreasing. F prime is still less than 0, f is decreasing. F prime is greater than 0, f is increasing. So at negative 1, the graph changes from increasing to decreasing. There's a relative max there. At 0, it's decreasing, then stays decreasing. So this is neither a min nor a max. It's neither one. And then the graph is decreasing, then increasing. 1 is a relative min. Okay, so again, not all critical numbers will be relative mins and relative maxes. They don't have to be. All right, and then now to summarize, this graph is increasing from negative infinity to negative 1 in the union with 1 to infinity because f prime is greater than 0. This graph is decreasing. Again, this is the graph of f from negative 1 to 0 in the union with 0 to 1 because f prime is less than 0. Okay, something strange is happening at 0, and we will talk about it. We just haven't gotten to it yet, but we're getting there. All right, it's coming up. There's a relative max at the point negative 1, comma. Well, I'd have to plug negative 1 into the original. So f of negative 1 is going to be negative 6 plus 10, so 4. because f prime changes from positive to negative. And then there's a relative min at 1 comma negative 4 because f prime changes from negative to positive. And there's my first derivative test analysis. There's all of it. Okay, not just the intervals of increasing, decreasing, but also the relative mins and relative maxes. All right, let's try this third one here. So now there's a denominator. So I'm going to use the quotient rule to derive this. All right, so we're going to have x minus 1 times 1 minus x times 1 over x minus 1 squared. So if I clean this up, I get x minus 1 minus x over x minus 1 squared, which is negative 1 over x minus 1 squared. Okay, so now I'm going to set this to 0 to find the critical numbers. That would mean the top would have to be 0, but it's not. It can't be. There's no values of x that'll make it 0. So I'm going to take the denominator now, set it to 0, because remember, this thing could be undefined, and if it's undefined, it's possible that you have a corner or like an absolute value graph where there's two different slopes, but there is a relative min there. So if I solve this, I get x equals 1. So there's one critical number to look at. It's just 1. Now, here's the thing, though. I want to know stuff about f prime so I can figure out something about f. I can pick test points here, but if you look at the derivative, look at what you have. The numerator is negative. The denominator, it doesn't matter what number you put in here. You're going to end up squaring it. So it's going to be a positive number down there no matter what. Okay? No matter what number you plug into f prime. So you have a negative divided by a positive. Well, the answer here is going to be negative. And the answer here is going to be negative. Because the value of x is actually irrelevant in this problem. So that means f is decreasing and f is still decreasing. So what can we conclude? This graph is never increasing at all. It's only decreasing. Okay, it's decreasing from negative infinity to 1 in union with 1 to infinity because f prime is less than 0. X equals 1, this point, is neither a min nor a max. And if you remember from last year or back in chapter 1, 1 is a discontinuity. It's a non-removable discontinuity. So there's a vertical asymptote at x equals 1. Okay? This is a non-removable discontinuity, vertical asymptote. All right, so it's neither a min nor a max. It's actually a vertical asymptote there. But again, just so you understand, graphs can change from increasing to decreasing across a vertical asymptote. Here's a good example. Here's just a simple example if you want to see something. Here's a graph that's increasing on the left side of the vertical asymptote and decreasing on the right-hand side. So you still have to consider this value, okay, on your number line in your analysis, because it is possible that the graph could change from increasing to decreasing. And at the end of the day, we want to graph f of x, right? We want to graph f of x. So we want as much information as we can get about it. Okay, here's the last one. I want to find the local extrema, increasing, decreasing, for f of x equals x to the 1/3 plus 1. All right, let's find the derivative of it. We get 1/3 x to the minus 2/3. Derivative of 1 is nothing. This x to the minus 2/3 has to come to the bottom. And now, again, we're going to set the problem equal to 0 to find the critical numbers. Well, 1 can't be 0. But the denominator, it can be 0. 3x to the 2/3 would have to equal 0. X is 0. So this is a critical number. So we're going to put it on our number line. So we have negative infinity, 0, and then positive infinity. We want to know the sign of f prime so we can figure out something about f. So now let's analyze this 1 over 3x to the 2/3. Okay, let's see how this thing works. X to the 2/3 is going to be 1 over 3 times x to the 1/3, but squared. We agree? Okay, it's going to end up squared down there. Okay, so when you have x to the 2/3, you can either write it as x to the 1/3 and square it, or you can write it as x squared, then do the 1/3 power of it. Either way, both of these equal 2/3 when you multiply, so it doesn't matter which way you do it. But here's the thing. The numerator is always positive. The denominator, again, is always positive, because whatever number you get here, you're going to square it. So this is bigger than 0. That's bigger than 0. So f is increasing here, increasing here. 0 is neither a min nor a max again. 0 is something else. We will talk about it. It is coming up. Okay, it is an important point on the graph. We just haven't seen what it is yet. All right, so this graph is increasing from negative infinity to 0 in the union with 0 to infinity because f prime is greater than 0. There are no relative mins and no relative maxes. Local min and local max is another way to say relative min and relative max. On the AP exam, they can use either one. Local and relative are the same thing. They use them interchangeably. The textbooks differ. Some textbooks use local, the others use relative. Okay, this is your example, or how the first derivative test works algebraically. All right, and as always, thanks for clicking.